Hello and welcome back to our notes on torque. Torque is a vector. Now, by saying it's a vector, we mean it has what? Okay. Hopefully you haven't forgotten this already. A vector has a direction. So we can't really say up, down, left, or right, because let's look at the top one. Here it's going down, here it's going up, but it's still going in the same direction. Okay, so what would we describe that direction as? I'll give you a hint. We don't have a lot of them that do this anymore, but most of them are digital. Okay, it's going to be clockwise and counterclockwise. So this bottom one here, that's the direction that a clock normally turns. So we're going to abbreviate that as CW. Okay, and then up here, this is opposite that. So we're going to abbreviate that as counterclockwise or CCW. Okay, so we'll be using that here and there. Something that you definitely need to know. So all right. So let's say we've got two 400 Newton kids balancing on a seesaw. They each weigh 400 newtons. This is going to balance. We've got their center of mass is going to be in the middle because they're equal masses. The pivot's in the middle. We know it should balance. Okay. Now, what would happen if that one kid slid in? Okay. What's going to happen to their side of the seesaw? Okay. Is it going to stay the same? Is it going to go up, or is it going to go down? Okay. It's going to go up. Okay. Even though we have the same forces on both sides, we don't have the same torque. Okay. And the center of mass wasn't over the pivot point anymore. So all this stuff connects. But we're going to be analyzing this in terms of torque right now. So here, this guy is pushing down on this. He's causing this to rotate like around like this, which is counterclockwise. Okay, well, he's not causing it to, but he would cause it. Okay. This guy on this side of the pivot, okay, he's trying to push this thing down, okay, where it's going to go around like this, which would be clockwise, okay, which would be clockwise. And so we've got, if we analyze the torque, so we've got the direction, counterclockwise and clockwise. This guy is the pivot point is here, okay, and this force is perpendicular to the lever arm, okay, so the torque is 400 newtons times 1 meter, gives me 400 newton meters of clock counterclockwise. Okay. Now here, we've got 400 newtons again, but we only have 0.5 meters. So when I multiply those together, I'm only going to get 200 newton meters. Okay, and that's counterclockwise, as we've already said. So what's going to be the net torque on this? Okay, well, they're going to cancel out partially, and we're going to have, so the 200 clockwise is going to cancel out 200 of the counterclockwise, and we're going to have 200 counterclockwise left over. Okay, so this counterclockwise is why his end pivots up, okay, because it's going clockwise, or counterclockwise, sorry. Okay, so in order to prevent an object from rotating, there can be no net torque. The net torque has got to be 0. Okay, or in other words, your torques clockwise have got to equal your torques counterclockwise. Okay, that'll be kind of a big thing here. So if there's no net torque, then an object does not do what? Does not rotate. Okay. Technically, it's more correct to say its rotational speed doesn't change, but we're good with what we got. Okay, if there's no net force on an object, then it does not what? It does not accelerate. Okay. Now here we've got a little kid, a big kid and a little kid, and they want a seesaw, so they want to balance. So who's got to move, or can they even balance? Okay, can they balance? Yeah, they can. Okay, who's got to move? Who's going to move in? Okay, towards the pivot point. The big kid or the little kid? All right. If you said big kid, you would be correct. Okay, the big kid's got to move in. And so let's see exactly how far away he's got to be. Okay, so 1 times 100 gives me 100. Okay, what can I multiply 400 by to get 100? 0.25. Okay, so so notice that this guy has 4 times the distance, and this guy has 4 times the force, and that's how they balance. That's how they balance. Okay. What is the upward force at the pivot point? Right here. 500 newtons. Forces have got to balance out too. Okay. If the seesaw balances, what's the weight of the other person? So we've got a 400 Newton person that's 0.75 meters away. So what's this guy's weight if they're balancing? Okay, so let's see. We've got a 400 Newton person on the left. He's got a lever arm of 0.75. We've got an unknown weight person who's 1 meter away. Okay, what is their mass? Okay, so what we're going to do is we're going to set the torque counterclockwise equal to the torques clockwise. Okay, so this is my counterclockwise side. So that's going to be 400. All right, force times lever arm times 0.75. So 400 times 0.75 equals, okay, force, which is unknown, times 1. Okay, so all we have to do is multiply the 400 times 0.75, which is 3/4, which is going to be 300. Okay, and you get F equals 300 newtons. Okay. All right. So pay attention. A lot of kids struggle with this. It doesn't have to be hard, but there'll be some where I say, where should we put the fulcrum? We've got 2 people on far ends. Okay, and what we're saying is, where should we put the fulcrum in order for them to balance? Well, who does the fulcrum have got to be closer to? It's got to be closer to the 400 Newton person. Okay, and this is the game I play when I do these. Okay, so this person has twice the force, which means in order to balance, this person has got to have twice the lever arm distance. So I know that this guy over here is going to have twice the lever arm distance of whatever this is. Okay, this is what I usually do. I call the short distance D. Okay, and since this distance has got to be twice whatever the left distance is, I call this 2D. Okay, so what fraction over from the right side is this? Is it 1/2? No, it's not. Okay, what is it? It's 1/3. All right, it's 1/3. So if this was a total distance of 6 meters, you'd say 1/3 of 6 is 2. That gives me 2, and this would be 4, and then I'd be done. Okay, so that's the game I play. All right. So here we've got a 500 Newton person and a 100 Newton person. They want to balance at the ends of a 3-meter seesaw. Where should the fulcrum be placed? Well, first off, generally I draw pictures for these. I strongly recommend that you draw pictures for any of your problems, to be honest. But these in particular, I think it's much more useful. So I know the fulcrum has got to be closer to the 500 Newton person. Okay, and since this person has got 5 times the force, okay, that means this side has got to be 5 times the distance. So I'll call this distance D. Okay, and then this distance 5D. Okay, and this is just, I think, the easiest way to do this. This distance right here is what fraction of the total length from here to here. Okay, it's not 1/5. It's 1/6 because this is a d over here too. So it's a total of 1/6 of the distance. So 1/6 of 3 meters means it's 0.5 meters. So d in this case is 0.5 meters from the left side. Okay? So correct the statement, which this is not a correct statement. It's a sometimes correct statement. Let me qualify that. An object balances when the same weight is on both sides of the pivot point. Okay, that is true sometimes, but not all the time. What would make this a true statement? When an object balances when the weight on either side create equal torques, or when the torques are the same on both sides. Okay, so there you go. Finish 8.4 and do concept worksheet 8-1 and enjoy your weekend.